Okay, in this lesson we are going to study enumerative combinatorics, which is just a fancy word for saying that we are going to be counting, and we're going to be coming up with different shortcuts for counting arrangements and groups of objects. So let's start off with an example. Let's say that we want to count. We've got these three guys here. We've got Prop, we've got Josh, and we've got Cy. And we want to count how many different ways that we can arrange these three people in order. Okay, so three people, we want to arrange them in order. So one way we can do it is kind of just like they're laid out now. Okay, so Prop, Josh, Cy. Another way we can do it is if we switch these two. So there's a second way. So Prop, Cy, Josh. And then we could switch these two. So now we've got Cy, Prop, Josh. That's 3. We could switch these two. That's 4. And let's see. There's 5 and 6. And I believe that we have 6 different ways that we can arrange these 3 people. Okay, so what if there was, let's throw in one more person. Let's throw in Appa. Okay, so now we've got 4. We want to arrange these 4 characters in, we want to see how many different unique arrangements, how many different unique orders. So now here's 1, and then here's 2, and I'll be honest with you, I don't know that I could keep concentrating on how many different arrangements there are. So let's look for a shortcut. Thankfully there is a shortcut, and it's called the multiplication principle of counting, or sometimes it's called the counting principle. Okay, this is in page 704 of your text. If that's not focusing, you can copy it down there. And honestly, though, this formula is not really useful. I just want you to know what it means, not necessarily what the formula says. So what it says is we can take the number of objects, and we'll call that n number of objects. And we want to think about how many different stages there are in this one event. So if we're looking at 4 objects and we've got 4 slots to fill in, so then we're looking at, for the first event, or the first stage, then we want to see, well, we've got 1, 2, 3, 4 different possibilities, four people to go in that first choice. So I'm going to jot that down. So that's a 4. Okay, so let's say we pick Appa to go in number 1. So then how many options do we have for the second slot? Well, now we've only got 3. Okay, so we're going to multiply how many options we have for that second stage, and let's say Josh goes in stage 2. Okay, so now for stage 3, we've got 2 options left. So we're going to multiply that product by 2. Let's say Cy goes in there. And for our last stage, we've only got 1 left. So multiply that by 1. And so this product is going to tell us exactly how many different arrangements of these 4 objects we can have. So 4 times 3 is 12, times 2 is 24. So there's 24 different ways. If we were to rearrange these, we could get 24 unique arrangements of these. All right, let's look at another example. And let's look at a license plate. Okay, so this is a standard North Carolina license plate. Used to be where they would typically come with 3 letters and 4 numbers, but you'll see them with any kind of combination of letters and numbers. So let's say that we want 7 letters or digits in our license plate. We want to know how many different arrangements of those 7 letters or digits. We're gonna rule out symbols, and there's no restriction to which letters or digits that we use. Okay, so they can be all A's, they can be all 5s, or they can be a combination of any of those. Okay, so let's think about it like we have 7 slots to fill. Okay, so how many letters are there? Well, there's 26 different letters, and there's 10 different digits, 1 through 9, and don't forget 0. So if we think about our number of options for our first stage, we've got 36 total options. So 36 is going to be our first factor. And then for our second stage, our second number or letter, well, they can repeat. So it doesn't matter if we use an A, we can just use an A again. So our number's not actually going to change for any of our stages or any of our choices. So we're going to have 7 choices and 36 options for each choice. So this is the same as 36 to the 7th power, which is, if you put that in your calculator, you get 78 approximately billion. Your calculator is going to give you a times e to the whatever, but it's about 78 billion options. So I'd say that no worry about running out of different unique license plates. So let's look at another option. Let's say there's still seven slots, 7 stages, but now when we use one letter or one number, then we can't repeat that letter or number on that license plate. Okay, so we've still got 36 options starting off. So for our first stage, we've got 36 choices. But now if we use, let's say, an A here, then we can't use an A anymore. So we used to have 26. Now we've got 25 letter choices plus the 10. So now we've got 35. Okay, for our second option, so we use some other letter or number. Let's say we use a 5. So now that's 1 less digit. So now we've got 34 options. For the third one, we use a different letter, and you can see the pattern. It's going to decrease by 1 for each stage. And when we find this product, that'll tell us the different number of unique arrangements of 7 letters or digits with no repeats. Okay, that's going to be about 42 billion. Okay, quite a bit different than our previous example. Okay, so let's get a little more realistic. Let's say we want it to look more like this license plate here. Okay, let's say we want 3 letters and then we want 4 digits. Okay. Well, so 3 letters, and again, no repeating. So for our first slot, we want a letter, so there's 26 letters to choose from. Let's say we use one, we can't use that anymore, so that gives us 25 options for the second letter. And then we've got 1 more letter, so now there's 2 less, so now there's just 24 options. Okay, so now we go into our 4 digits. So we start off, there's 10 digits, 10 choices we have to choose for our first number. We've already used 1, let's say we use that 2. So now we can't use a 2 anymore. There's 9 other options. We used a 4. Now there's 8 options. We used a 3. Now there are 7 options. So if we find that product, okay, plug that into your calculator, and we get about 78,624,000. Okay, so those are, again, that's the number of different arrangements of 3 letters and 4 digits, no repeating on a license plate. All right, so let's give this a name. And we're going to call these arrangements. Lost my permutations. Sorry. There we go. Permutations. Okay, so a permutation is an arrangement of n object in a specific order. Okay, and our shortcut we can use is there are n factorial permutations of a set of n objects. Okay, so before, a couple of these that we looked at for our characters was 3 times 2 times 1 and 4 times 3 times 2 times 1. So these are examples of factorials. You've probably seen these in a previous math class, but just in case, our factorial is symbolized by an exclamation point, and we're just multiplying each previous integer down to 1, or each previous whole number. Okay, so again, if we have, let's throw in a fifth character. We've got our 4, and then let's throw in Bilbo. So now we've got 5 characters. So this the number of permutations of these 5 objects, the number of arrangements. Okay, so again, note that the order is important in a permutation. Then we're going to have 5 factorial for these 5. So that's going to be 5 times 4 times 3 times 2 times 1, which is 120. Okay, in your calculator, you can do factorials. If you go ahead and plug in the 5 first, and then if you press the math key and cursor over to the probability menu, and number 4 is our exclamation point, that's our factorial. Press enter twice and we get our 120 answer. Okay, so let's look at some other permutations. Let's look at some words. Okay, so first word, Hamilton. All right, we want to count the number of words that can be made using all of the letters in the word Hamilton. Now, when I say words, they don't actually have to be definable words or really even make any sense. Just how many different arrangements of these letters can we make? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8 letters. So we're going to have 8 factorial. And using our calculator, 8 factorial gives us 40,320. So think about, there's 40,000, over 40,000 different words, make-believe or real words that you can make with the letters in Hamilton. All right, let's look at another one. Let's look at Baggins. All right, so let's count the number of letters. We got 1, 2, 3, 4, 5, 6, 7. So if we do 7 factorial, then we've got 5,040 different words that we can make with these 7 letters. But notice that in Baggins we've got 2 G's. Okay, I can't tell one G apart from another G. So while this is the number of permutations, we also want to consider the number of distinguishable permutations. Okay, distinguishable permutations are just different arrangements of these letters or objects or whatever we're working with that can be distinguished from one another. So if we switch these 2 G's around, then we have a different permutation, but we can't tell the difference because they both look alike. So distinguishable permutations, here is our book's formula for it. Again, I'm not real big on the formula part, but all we're going to do to find the difference in the actual permutations and the distinguishable permutations is we're going to divide that permutation by the number of copies. So we've got 2 copies of G, so that's going to be the number of copies factorial. Okay, so we're going to divide 5,040 by 2 factorial, which is just dividing by 2, because 2 times 1 is 2. So we're going to get 2,520. Okay, so the ones that we can distinguish from one another, which is what really counts, is 2,520. Okay, one more of those examples. Let's say we have the word Robertson. Okay, so in Robertson we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different letters, but we've got 2 R's, so we want to divide by 2 factorial because we can't distinguish between the 2 R's, and we've got 2 O's, so we want to have another factor of 2 factorial in the denominator. Okay, so finding that product and that quotient, we get 90,720. Okay, so let's look at our permutation counting formula. There's some symbols we can use for similar operations. Okay, we've got this symbolism, this NPR business here. So let's say that, and this is in your textbook as well. This is a good one to jot down from your textbook on page 706. Okay, so jot down this formula, page 706. All right, and it says if we have a different number of objects from the number of slots to fill. Okay, different number of objects from the number of slots to fill. So let's say we have our 5 characters, but let's say we're running a baseball team and we're trying to find positions right field, left field, and center field for our team. And we've got these 5 players to choose from. Okay, so a different number of slots to fill from the number of options. So in our formula NPR, N is the number of objects and R is the number of choices to make, or slots to fill, or stages. Okay, so the way we do that, according to our formula, is we take the number of objects factorial over objects minus choices factorial. Okay, so if we have 5 for our number of objects, and we have 3 positions to fill, then we've got 5p3. So we've got 5 factorial over 5 minus 3 factorial. So by hand, we've got 5 times 4 times 3 times 2 times 1. 5 minus 3 is 2, so 2 factorial is just 2 times 1. Okay, so simplifying, we've got 2 over 2 is 1, 1 over 1 is 1. So 5 times 4 is 20, times 3 is 60. So there would be 60 different permutations of these 5 players in these 3 positions. All right, another example. Same 5 characters. Now let's say that we are in a casting position and we are looking to cast the roles of Romeo and Juliet in a play. Okay, so Romeo and Juliet, 2 different roles. We've got 5 of our characters have made the cut, and they want to know which role they can possibly get, and we want to know how many different permutations, how many different arrangements could we have of Romeos and Juliets. So we've got 5 choices, we've got 2 roles to fill. Okay, so let's look at this one in our calculator. Okay, your calculator does this NPR format as well. If we put in our N value first, and then we go back to our probability menu, so press Math, cursor over to probability, and you probably saw it when we were doing factorials. Number 2 is our NPR option if you're using a 83 or 84, and then we want to plug in our R value. Okay, so we've got 5 NPR2, press enter, and this tells us that we have 20 different arrangements, 20 different permutations of our 5 characters in the roles of Romeo and Juliet. Okay, so one more quick topic called combinations. Okay, so we've talked about our fundamental counting principle. We've talked about permutations, so now let's talk about combinations. Let's say that we are looking to cast 4 extras in our play Romeo and Juliet. Okay, so 4 extras, they're just going to be in a group. They're just going to, I don't know, be sitting at a table when Romeo and Juliet are walking by. It's not real important who's where. It's just a group of 4 people. Okay, so this is different than a permutation, where if we were to choose these 4 and just maybe switch these around, it doesn't make any difference because they're all just going to be in one group. So this 4 would be a different group than this 4, but if they were just picked in a different order, it wouldn't make any difference because they're just going to be sitting at a table in a group. All right, so combinations. Our book also has a formula for combinations that you should know. This is a good formula from page 707. Okay, it's got similar notation to permutations. Okay, so we've got 4 extras. We've got our 5 characters here. So again, N is still the number of objects, and R is still the number of choices or stages. Okay, so for our problem, casting 4 extras in Romeo and Juliet from our 5 characters, we're going to have 5C4. Okay, we'll go straight to our calculator for this one. So we're going to do 5. Go into our math probability menu, and NCR is right underneath NPR. Plug in our number of choices, press enter, and it looks like there are only 5 different options for the casting director to make. Okay, one more example. Okay, so let's say that we are going to order a pizza from papajohns.com. All right, so you can order a pizza online, and they give you a little visual what your pizza looks like. They give you the type of toppings they offer. And let's say we can only afford 3 toppings. Okay, 3 toppings is plenty for us. So we want to see how many different types of pizzas we can make with 3 toppings from a choice of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 different options of toppings. Okay, so since the people at Papa John's are just going to kind of throw those 3 toppings on, the order that we choose them in on the website doesn't really matter. So this is going to be an example of a combination. So again, the number of objects, we've got 19 choices or options for our toppings, and we're going to choose 3 of those. Okay, so go into our calculator, 19, combination 3, and we get 939 different options. Okay, so that is combinations. So important thing to remember with combinations is that the order that we choose or that we make our choices does not matter. One of the most difficult parts of these permutations and combinations is being given a problem and trying to figure out if it's a permutation or a combination from the wording. So be real careful when you're reading the directions of the problems that you're given. I'm going to give you a couple of example problems for you to try in your notes and to bring back in class next time we meet. So the first one, going back to our license plate problems. Okay, I want you to do 2 different options. I want you to choose how many different license plate options if you had to choose 2 digits and then 5 letters. Okay, and you can repeat any number of digits or letters. Okay, and then the second one, let's number these. 1 and 2. Second one, you want to choose 6 letters and then 1 digit at the end with no repeats of letters or digits. Okay, so solve those at the end of your notes, and then also on page 707 in your text, example 6 has 3 great scenarios. Tell whether they're permutations or combinations, and then go ahead and figure out how many different either arrangements or groupings there are.